My name is Brian. I'm on the base chain team, and today I'm going to talk about how we're scaling the Ethereum state Trie. So bottom line up front, Base built a Trie database, TrieDB. This speeds up Ethereum state access from like a O of log squared n factor to an O of log n factor, amount of I/O operations for the number of Trie nodes being accessed and updated. And we do this by using a Trie-aware storage engine. Okay, so that was a lot of jargon. I'm going to unpack that a little bit. So the actual problem here is that our existing Ethereum nodes will store the Merkle-Patricia Trie on top of like a general purpose database. I guess that was spoken out a bit in the previous talk. And this ends up causing a lot of write amplification, poor cache locality, and so forth. And last year I actually gave a talk here where we benchmarked Reth and found that like your slowest blocks tend to be the ones that update the most storage or Trie nodes. So this is like a real problem for scaling the chain. So just a little refresher here. The Ethereum MPT or Merkle-Patricia Trie is where all the account and storage state is stored. This is like a state tree where every branch can have 16 children, stores the hash of these children, and that walks down to your leaf nodes, which are accounts, so like balance, nonce, and so forth. Except then your accounts that are contracts can also have their own storage Trie. So you have this like Trie of Tries. So sometimes you have like a USDC type contract that has a massive tree of its own, otherwise the leaf of another tree. So this is a pretty heavyweight data structure, but it does carry like incredibly useful attributes. It lets you succinctly prove the existence or non-existence of any state in the tree, as long as you can agree on the root hash. And this is like critical for L2s, light clients. That's like how we perform like a proof of the actual state, so you can safely withdraw your funds like back to the L1. So some of the attributes of this tree, because it has like a 16 wide branching factor, it ends up being very wide and very shallow in general. So even though your paths are like 64 nibbles per layer of the tree, you end up with like the vast majority of that branching at the very, very top. So like ostensibly, because of this branching factor, you should be able to store like most layers of the tree with only like all but the bottom two for only like 0.4% of the tree, which would let you cache the majority of the like paths for even a terabyte large tree in only like 4 gigs, which would be very easily fit in memory. But you have some like really wonky characteristics here. 32-byte catch-out caches multiplied by like 16 wide branches gets you these like pretty chunky branches that do not pack well into like I/O pages. And then realistically, like there's no way you can fit one of these branches plus 16 of its children that are max size into a single like I/O page. And again, it's a tree of trees. When we talk about caching like all but the bottom 2 layers, that's not really well defined when suddenly you encounter another massive tree below it. So let's quickly talk about like how this works in existing EL nodes. So Geth is like the canonical, well, like the classic ETH client, uses like a log structure merge tree for storing all of its data. The good, bad, and ugly is that like writes are usually fast because you're writing into like a write-ahead log. Reads kind of depend on the age of the entry you're accessing, so it hasn't been touched in a long time. It could be very slow. And then really the ugly is that the writes are amortized and periodically compacted. So if you incur a lot of debt, suddenly your node might be completely halted as it's flushing a lot of data around and shuffling around. And then caching is also like on a per item basis. So again, like things that haven't been touched in a while tend to be much slower to access. And then like how does this work with the actual Trie? So it stores these Trie nodes as like a key value pair in this database. So as you access the like root of the tree, and then look for its child, and then look for its child, and so forth. You're performing like log n searches through this tree, which each takes log n time. So that's like your squared factor. And then Reth kind of and Aragon improve upon this. So they split into multiple databases or multiple tables. So your like plain key value pairs, your accounts and storage are able to be looked up in only log time because they're stored in their own tree. But then so that helps with executing transactions quickly in the EVM. But then when you have to seal the block and compute the state root and intermediate nodes, you then have to go into this other table that has all the intermediate nodes, and you pay all the debt anyway. And there are a lot of optimizations, like was mentioned in the previous talk. But like it still has to, there's still some pretty bad worst case performance. So like in summary, you have these like great databases that unfortunately are just like a poor fit for the MPT. So like in the worst case, you might be looking at like 50 IO operations just to like update one storage slot. And the cache is just like not aware of the Trie structure, so you might have like really good best case performance and very poor worst case. And because again, it's a Merkle root, like you guaranteed have to update everything along the path whenever you change anything at the bottom. So we built this TrieDB. Really the novel, like the database itself is just Trie structured instead of being like a log structured merge tree or a B tree. It's not really how people typically build databases, but it's relevant here for Ethereum. So it's built out of Trie nodes, right? You have your account nodes, which are kind of leaves, but also sometimes they're roots of other trees. You have storage nodes, which are like true leaves at the very bottom. And then you have all your branches in between. And like branches end up pointing to children somewhere else on disk, and then also carry the hash of that child. And like we're using variable size branch factor right now so that you don't waste too much space where you have like only a couple children. And then we take all these branches or all these nodes and then we pack them into contiguous subtries and then put these on like 4 kilobyte pages. So that's like the minimum unit of IO. If you're reading from disk or writing from disk, you're gonna write one of these pages anyway. So it's good to keep neighbors of the tree on the same page so you can ideally reduce the amount of IO accesses as you traverse from top to bottom. So what this means is like your absolute worst case performance when you go from top to bottom is like log n IO operations. Just the absolute worst is the number of nodes along the way. And because we have all of our MPT data, all of our hashes, you can pretty much get a proof of state for the same cost as looking up the data, just by collecting that along the way. And then like within the pages themselves, we then take like a slotted page approach. So we have these pointers that grow from one end of the page and the cells that grow from the other end of the page. And that allows us to have like durable pointers to some place on disk, even though we can resize and move around the contents like as a branch grows or shrinks. And that just like has some pretty nice properties in terms of just like accelerating the way that we are constantly like increasing and decreasing the size of the tree. Mostly for storage, I guess, where it changes the most. So there's some interesting properties. Because we have these pages that represent subtries, if you're like updating a bunch of leaves at the same time, you might find yourself branching off to multiple children that are on different pages. And that like transitively gives us like a completely non-overlapping rest of the view of the disk. So you can perform writes and hashing like truly in parallel as you branch out through the tree. And this like also opens up the door for sharded storage. If we're like a little bit less latency sensitive, we can imagine like supporting vastly larger state tries than like what you would get from like a single high performance local disk. And we use a copy on write structure, so very inspired by like LMDB or MDBX. pages are cloned as you write to them. You have to write to everything along the path anyway, as we said from the Merkle tree. And you have to write full pages because like the constraints of the disk. So this is like a pretty low overhead solution. And what this gets you, though, is the ability to have many concurrent readers in a single writer. Readers can hold on to like a shadow fork of the entire tree, and then you only clean up those pages when there's no longer any readers that can access them. And this should be very good for parallel EVM execution, because you could have like many readers all doing concurrent reads from the same block state as you like then funnel out your state changes to like your single writer that can do hopefully like pipeline writing. And yes, as I mentioned earlier, we have this tree of trees. It's again pretty bad for like traditional caching approaches. So we actually like built like a custom like versioned LRU cache concept. This lets us like get pretty close to what I was saying about caching like all but the bottom couple layers of the tree. EVM has some guarantees where like you must access an account before any of its storage. So you might as well cache the skip pointer to that account every time you read it. Similarly, as you go down a couple levels of branching within either the top level or lower level trees, these are worth caching as well for a skip pointer. So ultimately, when you're actually reading any net new piece of state, like you're probably only going to do like 2 or 3 IOPS, which is like hopefully a pretty good outcome, even with like a very large tree. And kind of explain how this behavior works for this cache. Probably go back into this later. Skip forward. So we have some preliminary benchmarks. So opening up a new database, putting a bunch of accounts and storage into it, and then just like moving this file around somewhere else so that there's no IO or OS level cache. We get some pretty good single-threaded metrics here. So we can get like 400,000 account reads per second, which is like the equivalent of 1 gigagas a second. That's just like pure IO. And account updates, we're getting like close to 100K per second, which is a similar level of gas per second. A little bit lower on the storage so far, but again, this is all single-threaded, and well, that brings us to like what we're working on right now, which is like parallel writes, parallel hashing are all kind of enabled by this sub-trie structure. So we're currently looking into how to like optimally utilize IO queues and have a thread pool under the hood, which can do all of our recursive Kedge caching and like properly saturate disk writes. And it's currently memory mapped, which depending on how much you're into databases, it's like a pretty good hack, but it's not like necessarily what you want long term. So we are like building a custom buffer pool as well, which can also intentionally pin top parts of the trie into memory. And that can get us like async IO as well with like IOU ring. And then finally, just like doing a better job of organizing the pages. So when we need to split sub-tries versus merge them back together, just to make sure that we have like a can optimize for like either the best case or average case of how many pages you need to traverse from top to bottom. And we think this is like a pretty aligned with like the Ethereum roadmap. There's like 3 key EIPs that I think are either coming in the near future or at least being discussed. So with like delayed state root or delayed execution, we get to have this allows us to really lean into like async IO updates. This would allow us to like use like really remote storage, much more commodity hardware, and scale up the total state like to a much higher degree. And then like block access lists, which might be coming in Amsterdam early next year, will add to blocks like a list of all state that will be accessed. Because we have this tree structure again, we can perform like very fast fan out batch reads with like no redundancy. So you would be able to pipeline read all of your state in like a very, very quick fashion. And then finally, there's actually a discussion on like a unified binary tree. This is being sort of as the modern counter proposal to the Verkle tree. Instead of having this 16 wide tree of trees, you end up with a single binary tree. I mean, this is just like vastly better for our use case in that you have only one tree, like consistent depth, faster hashing, and just like much easier to pack subtrees together. So yeah, like in summary, like you can check out the repo. It's open source. It's still in active development. We're working on integrating this into Ref as soon as possible. And this should decrease the amount of IOPS required. So one, just getting much faster block execution when a lot of state is accessed, but also just like not needing to rely on having like truly bleeding edge NVMe, massive NVMe local disks. Should make it much easier for anyone to run an Ethereum or base node as all of these networks continue to scale. So happy to answer any questions about this.
Thank you. So let me put it this way. So let's say we have a block access list. Now we will be able to load every storage slot that you may need before calculation. And then we have delayed execution that you can basically move the write out from the critical path. Those kind of like orthogonal optimizations, kind of like making like optimizing trial DB, the DB for the trial less important. Would you think it that way?
I mean, it definitely helps. And like right now, the disk is like definitely on the critical path for your high scale EVM chains. Getting back the extra time from delayed execution, whether that be like a 2-second or 12-second slot time, is certainly huge. There's still like it really depends on who you are in the pipeline. So if you are building blocks, then block access lists don't help you. They're only coming from the block builder. Like even if you have plenty of time to perform like the state root calculation, we still think there's like a lot of benefits to having just much less IO dependency, far fewer IOPS, and then like the ability to shard this tree onto like many disks or like individual nodes.
Thank you.
Hi. On the question of memory mapping, have you thought of looking at a more dynamic structure where you evaluate the frequency distribution of state use and restructure the tree based on that? So the top moves, most frequently used state move to the top, which is stored in the fast disk, and the rest, sort of the longer tail, goes to the colder storage. Because the overall state is quite metastable, so this becomes very efficient on the hashing and reads as well.
Yeah, I can answer that question. So one is like we are trying to be completely compatible with Ethereum state tree. So we aren't, well, moving things around is only insofar as like how we're optimizing, I guess, the number of pages traversed or what's in the cache. But we do we are very concerned with like worst case performance. So like the unfortunate side effect of saying let's weight our cache entirely to what's accessed typically is that then you have certain like periods of traffic where either a ton of net new storage is written or stuff that hasn't been touched in years suddenly is accessed en masse. And like this is the kind of thing that we specifically want to make sure is not like an attack vector on any chain, because we're ultimately limited by like what is the worst case performance.
I can share some testing that we've done on that front. One more question is on the sort of the frontiers stuff is on the binary, unified binary tree. This is just a comment you might have not known. Back in the day, there was a project called Handshake, which pioneered sort of this idea of having the embedded, state tree database, which they, pushed out a thing called UrkelDB, and which basically using the binary tree, and they're using Redux as well. So it's something worth looking into, and might be very interesting because, they basically had a lot of similar ideas. And I can also like make some comments on that offline.
Cool. Yeah, happy to chat after this. I don't know if there was a question you want me to answer there, but. All right, I think this is our last question here.
Yeah, thanks for the great talk. Lots of details. Could you speak more about the decision to do the variable branch factor as opposed to the 16 fixed branch factor?
Because keys are typically like randomly distributed because we're using the hash of addresses or hash of storage slot, you end up with a natural like branching factor where towards the top of the tree you're using every single one of your children in a branch, and then as you progressively get further down, you end up with periods where there's only like two children to a branch or 3 children to a branch. So right now we're using power of 2 branching just because we don't have to reshuffle the size of the nodes too much. But it generally tends to be fairly stable depending on where you are in the tree. So just reclaiming some extra space so that we have to make fewer IO traversals along the way.